So this morning we have two topics. One is axis transformation. The other one is time-based control. Time-based control probably is the most theoretically it's most difficult to understand. So I'll try my best to actually explain that to you. So now let's start with the axis transformation. When we have this axis definition, no matter you do that through the axis definition or doing the kinematics doing the transformation between the motor and the axis, axis itself is actually reside in a one coordinate system. Okay, in that specific coordinate system, other than just using the scale factor on the axis definition to manipulate the relationship between the axis and the motor, the other way to actually manipulate the axis is using axis transformation. So this matrix actually represents the actual transformation between the command that you give in the motion program and the real outcome that PMAC will execute in the motion program. Meaning, if I have a input, let me do this. So this is the transformation matrix. This is your input with some bias term we call offset. And this is the real XYZ that will be executed. Okay? So this is just a small representation of this because we have 32 axes in one coordinate system. So for each coordinate system, you will have one of these. You can choose to use this or not. Okay, it's just a way to actually easier to get you the transformation. Why do we need the transformation? You will see. Let's just say that you have a cutting pattern like this. It's a square. It's a square like this. And you want to say, hey, I want to have the same pattern at here, but with an angle. Usually you will have to do is actually recalculate, because when you actually do the pattern like this, you have to know the corner coordinate, right? And then put that in your motion program. The same thing here, then you have to calculate this by yourself and then put this in motion program, right? But since that they are the same pattern, so we provide a tool that lets you just input the transformation with the rotation, with the scaling, with the offset, and now we will execute this for you directly. Okay? So that's the first thing to understand. We have 6 sets of this transformation. 4 sets of this transformation. Remember I talked about this coordinate system that we have. The Cartesian coordinate system, we have 4 of these. These are the XYZ, UVW, XXYYZZ, UUVW. These are the only 4 sets of coordinates that you can use with this transformation. That's why in this giant transformation matrix, other than these matrix, for these axes, others are just the diagonal element for scaling. Okay, so you can actually still do the scaling for the other axes other than these 4 sets, but these 4 sets can actually do rotation, 3D rotation transformation for you. Okay, so that's the first thing to know. After you understand this, then the next thing is how to actually set it up, because right now the process will be this: you set this up, give me the coefficient in each set, and then put it in, and later you just say, oh, I want to use this transformation in which coordinate system. That's the enable part. And after that, it's automatic in the background. So let's introduce the element. So as you can see in the previous slide, all the diagonal, we will actually have the scaling part. The scaling part is actually defined by this structure. It's called T data I, diagonal M. The T data, this T means the table I. So you can actually have a lot of different tables. M is the number of the axis for index. Let's go back to the previous slide so you can actually see that. So you can see that here, the indexing that we have for diagonal, we call Ka, Kb, Kc, and so on and so forth. This A represent in here is with the index 0. So that's why I wrote this. It's KLM. L0 is A, L1 is B, and so on and so forth, up to 31, because we have 32 axes. So from 0 to 31, we have all that. So that's the diagonal scaling. For the offset part, the bias part, that's on the very right-hand side here. For the offset, for each one of them, you will have one of the offset term. So, okay, this is how we define it. It's called T theta I bias M. So M is still the index from A to ZZ. Okay. These, for all the axes, you will have this. For this part, the 3-axis set of diagonal element, you will only have the 4 sets that I mentioned. So this is how we defined it. So T theta I UVW M, it's KSM. This SM is actually from 0 to 5, like this. This is how we arrange it. Okay? So for different sets, like UVW or XYZ, or UUVVW, XXYYZZ, we actually put that in the structure name, so you won't mess them up. Okay? But you have to remember the M index is actually start from here. Okay. So here we have the example. This is how we set up for the XYZ coordinate system set. You can see that this is the structure. This is the T theta I, whichever table you select, dot diagonal 6, because X is from 6, right? Because you have ABC, UVW, X, YZ, XX, YYZZ. So the XYZ is actually starting from 6, 7, and 8. And the first off diagonal term for this XY is this here. 0, 1, 2, 3, 4, 5. Okay. So this is just a little bit confusing, but well, you can map it with whatever I have in this slide. Okay. After you set it up, the rest is easy. How to use it? So you have this function called tSelect. TSEL. I is the number of the table you want to use. So you can create a lot of different tables, and then you can select which one you want to use. After the matrix is selected, then it will automatically apply the move for that. Just automatically use that. So whatever move you have input in your motion program, it will be inserted in here, and then multiplied by the matrix you define with the offset, and then this is the result that the PMAC will execute, actually. Okay? So here we actually provide the command that to deselect all the transformation matrices. So this is an easy way to actually deselect whichever matrix that you already apply to the current coordinate system. The core x.tselect will actually report a number of the current transformation matrix. If it report -1, that means no one is selected. Initialization here. Tint I. This one will actually normalize the matrix. Make it a unity matrix. What do I mean by that? This is a unity matrix. Oh, sorry. 0, 1, 0, 0, 1. This is a unity matrix because whatever you put in here will come out on the other side. Of course, it will set all the offset all to 0. Okay? Because this is the same thing as this. So it doesn't do anything. So usually before you actually put things into a matrix, we actually initialize it to make sure that, okay, there's nothing actually doing in the transformation matrix, and after that we put the number in. TDT, this one is it's not a function. This is a variable that we usually define. You can define something else, but this is just to validate that, okay, the initialization is working. So we internally have a checkup function say that, okay, if it's really initialized. If not, then you actually return 0 from this function. Okay, so I just put a variable here to actually get it out and then say, oh, check it to see if it's really actually initialized. Propagation function. This one is the multiplication between two transformations. Meaning, if you define two transformations, you will actually have, let's just say that this is my first transformation. And I have another one with a different matrix called M2, something like this. Okay? Of course, with the offset of 2. Let's just say that this is M1, this is D1, something like this. So if I want to get the result of the two transformation and then get it into one, this is the function that we use. So basically, this function is called tprop ijk. J and K are the two initial matrices that you want to multiply together. I is the one that will be the result. Okay? So here I say this, this will multiply T data J by T data K, and then put the result in T data I. Okay, so we usually do this trick, meaning if I put like 1, 1, 2 in here, that means 1 will be multiplied by 2, and then the result will be coming back to 1. So you multiply 1 by 2, and then you put that back in. Okay, that's the trick that we usually do for the incremental rotation or offset. And this is the formula that we have. So you can see if you go to the user's manual for this section, it will actually tell you, okay, if you multiply this to 2 together, the result term will be the multiplication for the two matrices that I defined over there, 1 and 2. And the offset will be 1 multiplied by offset 2 and then plus offset 1. Okay, I put this in the equation. So if you look into the user's manual, this is described in sentence, in words. Any questions so far? Yeah, we have to put this into a test to let you understand how this really works. So here are some examples that we have. The first one is the rotation. This is around z-axis. So we only define the turns in xy. Okay, because if you rotate around z-axis, the only thing that changes in the xy plane. Okay, so these are the only things that you need to define. So initially, I select transformation 1, and then I initialize transformation 2, and I put these transformation rotation data in transformation 2. Okay, and then I say tprop 1, 1, 2. So I multiply 1 by 2, and then put that back in 1. And so then 1 right now will be the transformation of this. Because I initialized 1 already, so 1 is like 1, 1, 1 at the diagonal, and then nothing happened over there. Okay, this is the usual way that we actually do incremental rotation, and so you don't have to. You can actually have different sets of angles, or you can actually do incremental angle. If you do this one more time, then you will have another relative rotation for this theta. Okay. Do you guys understand how this rotation metrics work? Okay, this is sine, cosine turn. Cosine turn is always at the diagonal. Sine turn is off diagonal, depending on which direction, clockwise or counterclockwise. Then you put different negative sign for that. This is cosine, sine, 0, cosine 1, 0, 0, sine. This is the rotation around z. So it's like this. And either you minus sign here or minus sign here, depending on the counterclockwise or clockwise rotation. Okay. So this is the rotation. The second one is the scaling. This is usually useful because when you want to actually change the unit of your system, then you can just apply this directly. You don't have to change the scale factor of your motor. Remember, we have this motor and axis relationship defined by axis definition. You say how many counts from motor is like 1 inch. Then later, if you want to change back to millimeter or even meter or feet, then you have to change that scale factor, right? No, not necessary. You just apply the rotation matrix. So you don't mess up with your original definition for axis definition scaling. You just apply this. So you can actually have two bottom. One, when you click, you want to use inch, then you apply one of the rotation scaling matrix, and it will actually do that for you. So whatever you input from your motion program, you don't have to scale in the motion program because we do that for you. Okay, so this is another useful use. Usually in CNC system, when you actually change from inch to millimeter, this is what we usually do inside PMAC. We have just have a matrix and then do the scaling for you. So it's the same process. I initialize one and then put these values in 2, and then I do T-prop 112. The other one is the offset. Same thing. So we only mess with the bias turn with some number that you give me, and I do T-prop 112. Okay? You can see that there's another command that's right after these. See here, the P-match? That's because you want to match the current motor with the axis position. Meaning you have to make sure that it actually really goes through the process to give you the correct axis position result. Okay? Have other people mentioned P-match before? Okay. P-match, if you actually send this command, even no matter it's online or in the program, it will actually execute forward kinematics or axis definition one more time for you to actually say, okay, P-match means position matching. So I want to actually calculate the current axis position through my current motor position. That's the P-match thing. So if you have kinematics, that will run through forward kinematics. If you have axis definition, it will actually run through axis definition. Okay? Because sometimes when you change coordinate system, the actual axis doesn't know. The actual calculation doesn't actually happen. So you need to make it happen using this command. Okay? Questions so far? No. Okay. This is some program that we have. You can actually try it. Let me see. What do we have? So let me explain this. So this is the result I have. Basically, what we are doing here is this. We have a cut from 0, 0 to 2000 and come back like this. So we are cutting a box. The goal is actually to cut the box with a 30-degree difference every time. And we execute that 3 times. So you will have 4 boxes. 1, 2, 3. So in the program, make sure that you have the correct definition for axis. And after that, I just do the program. So I declare a counter, the theta that I want to actually rotate the whole thing, number of cuts, and the TDT is the determining of the matrix that I want to check to see if it's really doing the axis definition transformation matrix correctly. I hope the motors which here shouldn't be necessary because before you run the motion program, you should home your motor. So here we are just actually having this because we don't want your motor to actually run all the way back to its home and start the program. So we start the program with homing, and then it will start right away. So linear ABS, absolute move, and this F feed rate and TATS, and we go back to 0. And then here we enable the getter. So when you actually pop out your plot program, this will actually do the plotting for you to gather the information. T-select -1, make sure that it's deselect for the first move. And then we do the cut. So this cut is basically the first cut that's along the XY X axis and Y axis, the normal one. And then after that, I do initialization on 1, put everything in 1, and then select 1 and p-match. So now, after this function, T-select 1, my axis transformation matrix is active. And then after that, I say increase the counter, and I do T theta plus equal 30. Meaning, initially, it's 0, right? It's 30, right? And after that, the first one will actually have the 30 degree in here. Once I have that, I increase the counter in here. So when it comes back, it will actually execute this part with 30 degree of rotation in here. Okay? And then since the theta has been increased to 30, the second time you get in, this will be 60 degree, and so on and so forth. Okay? So at the end, we will have a 90 degree because we executed for 4 times. Okay? So that's why we have this result in here.